Good friends, already we discussed about the illustration and also the numerical of exercise, and we discussed the sum also, the numerical asked in board exam. Now one illustration is still remaining, that is the 10.4. Generally this illustration or different part of this illustration may be asked for competitive exam like as the NEET and also would say. For that purpose today we are going to discuss this illustration. Now here, this illustration depends on Young's double slit experiment to obtain the interference pattern. Okay, in interference, here the some parameter, that means the physical quantity, the width of or the distance between the two slits, that is the small d, distance between the screen and slit, that is the capital D, and due to the change in this parameter or this physical quantity, what is the effect take place on the fringes? Today we are going to discuss this thing. So here the question is that what is the effect on the interference fringes in Young's double slit experiment due to each of the following? Now first question is that the screen is moved away from the slit. That is the slit, that is the screen. Initially we obtain the interference fringes from the screen. Now, the distance between the slit and screen increases. That means the screen is moved away. So what is the effect take place on the fringes? So here we know that the distance between the two fringes, that is denoted as beta. Beta is equal to lambda capital D upon small d. Lambda is the wavelength of light used. Capital D, distance between the screen and slit. While the small d is the separation between the two slits, because in Young's double slit experiment there are the two slits to obtain the coherent sources. The separation of these two slits is small d. Now, according to our question, if the screen is moved away from the slit, that means the capital D is increased. So lambda upon d, that is the angular separation of the fringes, is constant. Therefore, from this equation, beta is directly proportional to the distance between the slit and screen. So when the screen is moved away from a slit, D increases and beta also increases. According to this equation, beta proportional to the capital D. And beta will increases, hence the interference fringes becomes the wider. That means the separation between the two fringes is increases due to the increase in slit and distance between the slit and screen. Clear this? Okay. So this is the first part. As the distance between the screen and slit is increased, so separation between the two fringes also going to increase. That means the interference pattern becomes the wider. Now second part, the source is replaced by another source of wavelength, shorter wavelength, or the wavelength shorter. So what's happened? Again, according to this equation, beta is equal to lambda capital D upon D. Here beta is directly proportional to the wavelength. As the wavelength is decreases, so the separation between the two fringes is also decreases. So wavelength becomes the shorter, lambda will decreases, and hence the fringe width beta also decreases. That means the two fringes becomes very close. Whether we obtain the two fringes or the separation between the two fringes is decreases. Now, third is the separation between the two slits is increased. Separation between the two slits, that means the S1 and that is the S2. This distance D. This D is increased, what's happened? S1 and S2 becomes being at high distance. Separation between the two slits increases, therefore the D increases. Again, according to the equation 1, beta is equal to lambda capital D upon small d. Beta, separation of the fringes is inversely proportional to the 1 upon d. Here, the separation between the two slits small d increases, what's happened? The fringe width beta will decrease, and hence the fringes becomes the narrow. Therefore, in interference pattern, the two fringes are often very close to each other. Now, Next question is that the source move closer to the double slit. Now in Young's double slit experiment, that is the source S. Now here the double slit are used. If this distance is decreases, that means the source is being towards the slit S1 and S2. What's happened? Actually, that is not represented by the equation, but the effect is obtained on the screen. So what is the effect? When the source is moved close to the slit, the bright and dark fringes are merging to each other. That means both are overlapping each other. And the sharpness of the fringes becomes the small. That means the sharpness of the fringes decreases when the source is very close to the slit. So fringes are disappearing on the screen, and screen is illuminated with every intensity of the light. Again, what's happened here? When the source is moved close to the double slit. So what's happened? When the source is moved close to the double slit, the bright and dark fringes are merging each other. That means the overlapping each other. So the sharpness of the fringes decreases. We can't separate each slit. Therefore, the sharpness is decreases. When the source is very close to the double slit, what's happened? The fringes disappear and the screen is illuminated with the very intensity of the light. So, whole screen is shown the white with the very intensity of the incident light. Now, one more thing. If the separation between the source and slit is not very close, at that time what's happened? The width of the fringes does not depend on the distance between the source and slit. If the minor change take place in the distance between the source and slit, there is no effect take place in the width of the fringes, because width of the fringes is not depends on the distance of the source and slit. Clear? So that is the answer. Now next is the width of the source slit is increased. That means if the source is increased, width of the source is increased, what's happened? So answer is the same as above. That means when the source is moved, that means the width of the source is increased. So what's happened? The fringes are merging into each other. That means the bright and dark fringes are merging to each other. And if the width of the source is very large, at that time, what's happened? The fringes are disappear and screen is shown, or the screen is illuminated with the average intensity of the light. Again, the width of the source slit is increased, so the fringes are merging each other, and the sharpness of the fringes decreases. Sharpness of the fringes decreases. And when the width of the source is quite more, at the time the fringes are disappear and screen is illuminated with the very intensity of incident light. Now the last portion. In stationary interference or in Young's double slit experiment, we are using the monochromatic light. That means the source with single wavelength. Generally, we are using the yellow or the orange light, sodium light. If the monochromatic source is replaced by a source of the white light, so instead of this monochromatic light, that means the sodium lamp, we are using the white light. What's happening? When the source of light is used, when the source of the white light is used, the interference pattern of all colors overlap on each other, and the central bright fringes of all color occurs at the same point. Therefore, central bright fringes show on the white. So now listen, white light is made up of the 7 color. So due to the interference phenomena, all the colors are overlap on each other, and as a result, the central bright fringes of all color formed at the same point. Therefore, central maxima is shown the right. Okay. And the fringes close to the central maxima appears red, and as we go away from the central maxima, the fringes are shown the bluish. That means here not the dark bad fringes obtained, but here the fringes obtained with colorful. And red color is very close to the central maxima, and at far distance the fringes shown the bluish. Again, if monochromatic source is replaced by a source of the white light, so what's happened? When the source of the white light is used, the interference pattern of all colors overlap on each other. So the sharpness of the fringes are decreases. The central bright fringes of all colors occurs at the same point. Therefore, the central fringes becomes the white. Now, close to the central fringe, we obtain the red fringes, and at far distance, the fringes becomes the bluish. So, friends, that is the answer of illustration number 10.4. So, any portion may be asked for the 1 mark question. Here it is. Okay. Now friends, the numerical asked in board exam, that is the asked in 2017. What is given? A plane polarized light incident normally on a tourmaline plane. Its E vector makes an angle 60-degree with optics axis of the plane. Find the percentage difference between initial and final maximum value of E vector. So here the plane polarized light is incident on a tourmaline plane, and its E vector makes the angle with the 60-degree angle with the axis of the tourmaline plane. We have to find out the difference between the initial and final maximum value of E vector. So here we are using the Ballas law. The intensity of transmitted light I is equal to I0 cos square theta. From Ballas law, I is equal to I0 cos square theta. Here theta is the 60-degree. Therefore, I upon I0 is equal to cos square theta is equal to cos square 60-degree. Cos 60, 1 by 2, and square of this, therefore 1 by 4. I upon I0 is equal to 1 by 4. That is equation 1. But we know that the intensity is directly proportional to the square of amplitude. So I is proportional to the square. So from equation 1, here we substitute the value this I, therefore is square I0 E0 square is equal to 1 by 4. Therefore, E0 upon E, first we add E upon E0 is equal to 1 by 2. We make the square root on both sides. Therefore, E0 upon E. Take the reciprocal of this, 2 upon 1. E0 is the initial amplitude, E is the final amplitude of oscillation of electric field vector. Now we require the percentage value. So initial minus final upon final value. Therefore, E0 minus E upon E is equal to this side. What's happened? 1 minus 1 by 2. 1 minus 1 by 2 upon 1. 1 minus 1 by 2 upon 1. Therefore, 1 by 2. Percentage value is 0 minus E upon E multiply by 100% is equal to 1 by 200%. 1 by 2 is equal to 0.5 into 100. So it's equal to 50% is the answer. So 50% answer is the difference between initial and final maximum value of the E vector. E0 minus E upon E. Here is. So there is our answer. Percentage difference. Again, from Malus law, I is equal to I0 cos square theta. Take the ratio of the intensity I upon I0 is equal to cos square theta. Theta is given 60 degree. Therefore, cos square 60. Cos 60 is equal to 1 by 2 and square of this, that is the 1 by 4. I upon I0 is equal to 1 by 4. But we know that intensity of the light is directly proportional to the square of amplitude of oscillation of E vector. Therefore, I proportional to the square. Instead of the I can add the square. Instead of the I0, initial intensity or the intensity of the plane polarized light which is incident on a tourmaline plate. Therefore, E square upon E0 square is equal to 1 by 4. Take the square root. E upon E0 is equal to 1 by 3. Now, E upon E0 is equal to 1 by 2. Therefore, E0 minus E upon E. Therefore, 1 minus 1 by 2 upon 1 is equal to 1 by 2. Therefore, E0 minus E upon E, percentage difference is equal to 1 by 2 into 100%. Clear this? So it's equal to 50%. So I think here the E minus E0, E minus E0 upon T. Okay. So upon E0. Therefore, we obtain the 1, 2 minus 2 just move. Because there is a right here E is equal to what? Value 1. E0 minus 2 upon 2. Therefore, minus 1 by 2. So here we are going to find out the percentage. Therefore, we take the mode. So there is the positive. Therefore, 1 by 2, 100%. So it's equal to this value. E minus E0 upon E0. So there is the percentage difference in E vector. Now next is next numerical is also important. In Young's experiment, fifth bright fringe produced by light of 4,000 angstroms. That means as lambda 1 is equal to 4,000 angstrom, at that time the involved is equal to fifth bright fringe is open at some point on the screen. Now, on this point, superpose on the fourth bright fringe of unknown wavelength. Now, lambda 2 is unknown. We have to find out for this unknown wavelength, N2 is equal to fourth bright fringes are superposed on this point. So we have to find out the unknown wavelength. So what it suggests? So on the screen, there is the screen. For wavelength lambda 1, here the fifth bright fringes is obtained. That is the N is equal to 0. 1, 2, 3, 4, and 5. N is equal to 5 for lambda 1. For lambda 1. For lambda 2, 1, 2, 3, and 4. N is equal to 4 bright fringes are superposed for lambda 2. This distance is same. The distance is same. The distance between two consecutive back fringes is beta 1 for lambda 1. Suppose the distance between two consecutive back fringes is beta 1 for lambda 1 and beta 2 for wavelength lambda and distance of n1 back fringes from central maxima is same as distance of n-tooth back fringes from central maxima. Therefore, n1 beta 1 is equal to n2 beta 2. Therefore, n1 lambda 1 d upon small d is equal to n2 lambda 2 d upon small d. That is cancelled. Therefore, n1 lambda 1 is equal to n2 lambda 2. We require the lambda 2. n1 lambda 1 upon n2. n1 fifth lambda 1 4,000 angstrom upon 4. Therefore, lambda 2 is 5,000 angstrom. So where is the numerical, but our concept must be clear about this. On the screen, for wavelength lambda 1, fifth back fringes is obtained at whatever the distance. The same distance for unknown wavelength, the fourth back fringes is obtained. Therefore, the distance of n1 and n2 back fringes is same to the central maximum. So n1 into beta 1 is equal to n2 into beta 2. We know that the distance between the two consecutive back fringes is lambda d upon small d. So using this concept, d upon d is cancelled. Therefore, n1 lambda 1 is equal to n2 lambda 2. Therefore, lambda 2 is equal to n1 lambda 1 upon n2. Thus, we obtain the unknown wavelength is 5,000 angstrom. Now, the last numerical that is asked in 2014 and 2015. In Young's experiment, the distance between the two slits is 1 millimeter and distance between the two consecutive back fringes is 0.03 centimeter. So here what is given? Small d is given the 1 millimeter, therefore 0.1 centimeter. And distance between the two consecutive back fringes is 0.03 centimeter. Therefore, for d1 is equal to d, beta 1 is 0.03 centimeter. And for d2 is equal to d plus 50. Beta 2 is equal to twice d1. Twice d1. Now, on displacing the screen away from the slit by 50 centimeter, the distance between the two consecutive back fringes becomes the double. Find the wavelength of light used. For this purpose here, we are writing the answer like this way. When the distance between the slit and screen is d, when the distance between slit and screen is d. Okay, we have the next word. require the sufficient space. Clear these two numerical? Okay, now in this numerical, Young's experiment, the distance between the two slits is 1 millimeter. That is given in millimeter, we convert into the centimeter, 0.1 centimeter. And distance between the two consecutive bed fringes is 0.03 centimeter. Therefore, for given distance between the slit and screen is suppose the D. At that time the beta 1 distance between the separation of the consecutive bed fringes is 0.03 centimeter. Now, on displacing the screen away from the slit by 50 centimeter, that means we change, that is the slit, double slit. Initial screen is at here, so that this distance is D1 is equal to D. At the time the bed fringes are obtained like this way. This separation is beta 1. Is beta. Now, the slit is placed at here. This distance is D2 is equal to D plus 50 centimeter. At that time, the bed fringes becomes the double. Separation is double. That this beta 2 is equal to beta 1. Find the wavelength of the light. That is our S1, that is our S2. This separation is small d. For that purpose, when the distance between slits and screen is d, the distance between two consecutive bed fringes is beta 1. Beta 1 is equal to lambda d1 upon small d. And here we take this distance d1 as d. Now, the screen is moved away by 50 centimeter from the slit. So D2 is equal to D plus 50 centimeter. Then distance between two consecutive bed fringes is D2 is equal to twice D1 is equal to lambda D2 upon D. Therefore, D2 minus D1 is equal to lambda D2 minus upon D minus lambda D1 upon D. So lambda upon D is common, D2 minus D1 is equal to lambda upon D, here D plus 50 minus D. D cancel, therefore 50 lambda upon D. Now B2 is given, that is the 2B1 minus B. Therefore beta 1 is equal to 50 lambda upon D. Therefore, lambda is equal to beta 1 d upon 50. Beta 1 is given, that is the 0.03. D is 0.1 centimeter upon 50. Therefore, we obtain the wavelength is 6000 angstrom. The wavelength of the light used in this experiment is 6000 angstrom. So this numerical 2 times asked in board exam 2014 and 15. So here this chapter 10 is completed with the numerical, where we also calculate the some numerical asked in also board exam. So a concept must be clear that any numerical on the base of the Young's experiment asked, we must be able to calculate